Welcome to topic 3101, Ecological Flood Risk Assessment and Nature-Based Solutions. In the next 20 minutes we'll treat urban flooding as a socio-ecological risk, not just a hydraulic problem. The point is practical. How do you move from a messy, uncertain flood context to defensible planning choices, and do it in a way that is aligned with ecological planning principles, climate adaptation frameworks, and equity? We'll use a simple risk structure: hazard, exposure, and vulnerability. Then look at the tool spectrum: rapid GIS screening, hydraulic models, and fast mapping methods that can support quick prioritization. We'll close by translating risk insights into green-blue infrastructure and circular water strategies, grounded with two best-case examples. Keep one discipline in mind throughout. If a claim cannot be supported by evidence or bounded uncertainty, we downgrade it, we qualify it, or we don't make it. Here is the roadmap for the session. First, we establish why urban flooding matters specifically for planners. It disrupts mobility, services, and recovery, and it interacts with land use and ecological networks. Second, we refresh ecological planning concepts and define nature-based solutions: what they are, what they are not, and why they are often multifunctional by design. Third, we formalize risk through hazard, exposure, and vulnerability so that everyone in an interdisciplinary team uses the same mental model. Then we review the main tool pathways: GIS-based susceptibility screening, coupled hydraulic modeling, and fast mapping, approaches that trade detail for speed. After that we focus on what makes a map decision ready: explicit assumptions, scenario framing, and clear limits. We finish with CS001 and CS002, then summarize the key takeaways and point you to the references. These learning objectives are the contract for this topic. First, you should be able to explain core ecological approaches in landscape planning, especially connectivity, ecosystem services, and how landscape structure shapes hazards and recovery. Second, you should be able to interpret climate adaptation policies and planning frameworks, including how they shape priorities, accountability, and no-regrets actions. Third, you should be able to analyze ecological risks using tools such as GIS for screening, BIM for asset understanding, and parametric workflows for exploring alternatives. Fourth, you should be able to design nature-based solutions and multifunctional green infrastructure models, with explicit attention to water management and circularity. Finally, you should be able to advocate for interdisciplinary and inclusive approaches, because flood risk management fails most often at the implementation layer, where governance, maintenance, and vulnerable groups are ignored. Why does urban flooding matter for planners? Because cities are not just surfaces that get wet, they are networks. Flood impacts cascade. A flooded underpass can sever emergency access. A submerged transformer can trigger local outages. Closed roads can isolate neighborhoods. Urban flooding is often pluvial, rainfall overwhelms drainage, or it can be fluvial, coastal, or groundwater related, but the planning relevance is the same: land cover, imperviousness, drainage capacity, and topography interact with exposure and social vulnerability. Climate change adds an extra layer of uncertainty, not as a single number but as a shift in extremes and sequences of events. From an ecological planning view, the question becomes: how can landscape systems store, slow, infiltrate, and safely route water, while also improving urban habitat and thermal comfort? Our goal is not perfect prediction, it is defensible prioritization and robust interventions. Ecological planning starts with the idea that cities sit inside landscapes, not outside them. That means we pay attention to ecological networks, catchments, soils, vegetation, and connectivity as real infrastructure. In practice, ecological planning asks, what landscape functions are degraded, and how can planning restore them in ways that also reduce risk? For flooding, three functions matter immediately: storage, infiltration, and safe conveyance. Storage can be provided by wetlands, parks, retention basins, and even streets designed as temporary channels. Infiltration depends on soil and permeability and can be improved through green infrastructure and reduced compaction. Safe conveyance means that when water must move, it moves along routes that minimize damage. This is where corridors and urban form matter. Ecological planning also forces trade-off thinking. Adding a new built surface changes runoff. Removing green connectivity can reduce recovery capacity. Nature-based solutions, NBS, are actions that protect, manage, or restore ecosystems in ways that address societal challenges and deliver human well-being and biodiversity benefits. In flood contexts, NBS overlaps with green-blue infrastructure, permeable landscapes, restored waterways, wetlands, urban forests, and distributed retention features that work as a system. 2 caution points. First, NBS is not decorative green. It must have a clearly defined function, performance logic, and maintenance plan. Second, NBS is not automatically equitable. If it triggers displacement or ignores accessibility, it can create new risks. When used well, NBS tends to be multifunctional. It reduces runoff peaks, improves water quality, supports habitat, and can reduce heat stress. Because these benefits depend on context, we treat NBS planning as scenario-based decision support rather than universal promises. Now we formalize risk using a structure that works in planning meetings: hazard, exposure, and vulnerability. Hazard is the physical event or process, such as intense rainfall, overflow from a river, or surface flow paths. Exposure is what is in harm's way: people, buildings, critical facilities, and the networks that keep a city functioning. Vulnerability is how sensitive those exposed elements are and how much capacity exists to anticipate, cope, and recover. This is where social conditions, building fragility, and service redundancy enter the analysis. The key insight is that risk is not solved by hazard mapping alone. 2 districts can have similar hazard levels but radically different outcomes because exposure density and vulnerability differ. So the workflow is: map hazard plausibly, characterize exposure explicitly, and treat vulnerability and equity as first-class inputs. That is how you produce decision-ready outputs instead of pretty maps. GIS screening is the fastest path to a first-pass susceptibility map, especially when detailed hydraulic modeling is not feasible. A common approach is terrain-based screening, using a digital elevation model to infer where water will accumulate and flow. Indices such as local depressions, flow accumulation, slope, and the hand concept, height above the nearest drainage, help identify areas that are topographically predisposed to inundation. This is not a replacement for hydrodynamic simulation, it is triage. It lets you rank areas for deeper study and it helps communicate where structural measures and NBS might be most effective. Quality control matters here. Resolution, sinks, and drainage enforcement can change patterns dramatically. Good practice is to present screening outputs as susceptibility, rather than flood depth, and to pair the map with a clear statement of assumptions, data sources, and known limitations. Beyond screening, we have a spectrum of hydrologic and hydraulic modeling options. Hydrologic models focus on rainfall runoff transformation, how much water becomes runoff and when. Hydraulic models focus on flow routing, how water moves through channels, pipes, and overland surfaces. In urban contexts, modeling often involves a coupled approach: a drainage network representation plus surface flow, which can be one-dimensional, two-dimensional, or a mix. The more detailed the model, the higher the demands for data, calibration, and computational time. For planning, the question is not, what is the best model in theory, but, what model is credible for the decision and the available evidence? Simple conceptual models can be strong for scenario comparison. Detailed models can be strong for design sizing, but only if calibration and validation are feasible. Our job is to choose a modeling level that matches the stakes, and to document uncertainty so the results remain defensible. Scenario thinking is the bridge between models and planning decisions. In flood risk work, scenarios often involve rainfall design events, land use change, drainage upgrades, or NBS adoption levels. A design storm is simply a standardized rainfall pattern used to test system response. It is not a prophecy. Because climate and urbanization evolve, a defensible practice is to test multiple scenarios rather than rely on a single assumed event. For example, you might compare current conditions to a future stress scenario, or baseline drainage to a case with distributed retention. Even without numbers, the discipline is the same. Define the scenario inputs clearly, run the same method across them, and compare outputs. In planning, you want robust choices, interventions that reduce risk across plausible futures, rather than fragile choices that only work under one set of assumptions. Fast mapping methods aim to produce useful flood maps quickly, especially when detailed modeling is too slow or data-hungry. Machine learning approaches, such as random forest models, can learn relationships between observed flood patterns and predictor variables like topography, land cover, drainage density, and rainfall characteristics. The advantage is speed and the ability to integrate many variables. The risk is transferability. Models can perform well in one city or event but fail when the context shifts. Therefore, we treat fast mapping as decision support for prioritization, not as an authoritative depth map. Best practice includes transparent feature selection, clear training and validation strategy, and conservative interpretation. From a planning perspective, fast mapping can help identify hotspots for site visits, community reporting, and targeted NBS interventions, while a smaller number of locations are selected for deeper hydraulic analysis. Exposure is often where flood risk becomes concrete. It includes obvious elements like buildings and critical facilities, but planners should also treat mobility and activity as exposure, because cities function through movement. A road segment that is frequently blocked can cause disproportionate disruption, even if flood depths are not extreme. In practice, exposure layers can include population proxies, schools and hospitals, public transport nodes, emergency routes, and economic activity indicators. One defensible approach, used in the CS001 case study, is to aggregate exposure information to a regular grid so that multiple data sources can be combined consistently. Exposure also includes temporal dynamics. Commuter patterns differ by time of day. Vulnerable groups may be concentrated at particular times. Planning outputs should therefore clarify what exposure represents: residents, daily population, or critical service dependence. Vulnerability is where technical flood mapping meets ethics and governance. It covers both physical sensitivity, building types, infrastructure fragility, and social vulnerability, income, age, disability, language barriers, and access to services. Two principles matter. First, vulnerability is not who is weak, it is a system property shaped by policy, investment, and service distribution. Second, vulnerability mapping can be misused if it stigmatizes communities or ignores local knowledge. An inclusive approach means engaging stakeholders, checking assumptions against community experience, and designing interventions that improve access rather than displace risk. In the hazard exposure vulnerability structure, vulnerability also includes adaptive capacity, early warning, evacuation routes, insurance, social networks, and recovery support. From a nature-based solutions perspective, equity requires that benefits, cooling, access to green space, water quality, are distributed fairly, and that maintenance responsibilities are realistic. How do we turn risk maps into decision support? The key is to translate spatial information into choices, priorities, and design criteria. First, define the decision. Are we prioritizing neighborhoods for intervention, sizing retention, protecting critical routes, or targeting retrofits? Second, define what success means: reduced disruption, reduced damages, improved ecosystem function, or a combination. Third, create a transparent prioritization logic. That might be a multi-criteria assessment where hazard, exposure, and vulnerability layers are combined with explicit weights, or it might be a rule-based approach for critical facilities. Fourth, document uncertainty and avoid over-precision. Decision support is about ranking and robustness. Finally, produce outputs that decision-makers can use: a short list of hotspots, a set of candidate corridors for green-blue networks, and a clear explanation of assumptions. One practical extension is to connect map outputs to asset information. BIM or asset registers can encode critical elevations, access constraints, and service dependencies, while parametric workflows can generate and compare intervention layouts under the same rules. Now we shift from assessment to action, the green-blue infrastructure toolkit. Think of interventions as mechanisms, not objects. Mechanisms include storing water temporarily, slowing flow, infiltrating where safe, and routing excess water along low-damage pathways. Toolbox elements include bioswales and rain gardens along streets, permeable pavements in appropriate contexts, detention and retention basins, restored floodplains, constructed wetlands, daylighted streams, and urban forests that intercept rainfall and improve soil structure over time. In dense areas, green roofs and courtyards can contribute distributed retention, even if they cannot solve extreme events alone. A planning quality proposal matches tools to place: upstream storage, mid-catchment infiltration, and downstream safe conveyance, aligned with ecological corridors. Because each element has limits, we evaluate them as a system using scenarios and map-based prioritization. Circular water management extends the toolkit by treating stormwater as a resource, within safety and water quality limits. Circularity means reducing demand, capturing water where it falls, reusing it for non-potable needs, and infiltrating or discharging it safely. At neighborhood scale, this can involve rainwater harvesting, decentralized detention, and greywater reuse strategies that reduce pressure on drainage networks during storms. At landscape scale, it means restoring storage in wetlands and soils so that water is retained in the system longer. Important caveat: circular strategies must respect contamination risks and groundwater constraints, so the design must be site-specific. From a resilience perspective, circular water systems can add redundancy. If one part fails, others still provide partial function. In planning terms, circular water management becomes a set of design rules and incentives, required retention volumes, green coverage targets, or performance-based credits, always tied back to risk reduction goals. Planning is not only technical, it is institutional. This slide connects our work to policy and framework alignment. At the EU level, documents like the European Green Deal and the EU Adaptation Strategy emphasize resilience, ecosystem restoration, and risk-informed investment. For a project like EPD-Net, alignment matters because it makes learning outcomes transferable and because it helps justify intervention choices to funders and stakeholders. Practically, alignment means using consistent terminology, documenting risk and co-benefits, and designing interventions that are auditable. It also means avoiding maladaptation, actions that reduce risk in one place but increase it elsewhere, or actions that create long-term maintenance burdens that cities cannot sustain. Nature-based solutions standards, such as those proposed by IUCN, reinforce this discipline by requiring clear objectives, stakeholder engagement, and performance monitoring. Let's ground the topic in the two required best cases. CS001 demonstrates a flood risk mapping approach that combines a terrain-based susceptibility indicator, HAND, with exposure information that includes both resident population and mobility or activity data aggregated to a regular grid. Importantly, it also considers observed disruption data, such as records of flood-related roadblocks, to connect hazard to real functional impacts. The lesson is that decision-ready maps often integrate mobility, not only depth. CS002 demonstrates a modeling approach that couples SWMM for drainage and MIC-urban for surface inundation, then uses scenarios to evaluate mitigation options, including a detention pond concept. The lesson here is about tool pairing. A network model plus a surface representation can reveal where drainage upgrades or distributed storage will shift peaks and reduce flooded extents. Across both cases, the common thread is discipline, explicit assumptions, scenario comparison, and outputs designed to support planning choices, not just model performance. To summarize, ecological planning helps us treat flood risk as a landscape and network problem, not a single discipline calculation. Policy frameworks guide priorities and accountability, but the real work is translating them into transparent decision criteria. On tools, GIS screening is powerful for triage. Coupled models are valuable for sizing and detailed design where calibration is feasible, and fast mapping can support rapid prioritization when used conservatively. Nature-based solutions and green-blue infrastructure reduce flood risk while delivering ecological co-benefits, but only when objectives, contexts, and maintenance are explicit. Finally, interdisciplinary and inclusive implementation is not soft, it is risk control. Interventions fail when communities are excluded, responsibilities are unclear, or benefits and burdens are uneven. If you carry one habit from this topic, let it be this. Write down assumptions, test scenarios, communicate uncertainty, and avoid overclaiming.